So let's do some physics with a little bit of classical relativity. So in particular, I'm going to think about a collision, and while we're thinking about a collision, traditionally a collision problem includes thinking about momentum in the problem as well as energy in the problem. And in these collision problems, it's interesting to consider the physics associated with momentum and energy. Um, I, it maybe goes without saying, or maybe you've heard it before, but the point is momentum and energy in and of themselves, they're interesting things to define, but what makes them particularly interesting is the physics of momentum and energy. And the physics is based on a conservation principle. So the conservation of energy and the conservation of the vector momentum is the big deal. So let's look at conservation of energy and momentum with respect to classical relativity. And so what we're going to do amounts to what actually Einstein's kind of famous for doing this, but a lot of physicists and a lot of philosophers, it's a basic idea or a basic thing to do called a thought experiment. We're going to have a thought experiment. And so when you do thought experiments, there are going to be like certain kind of unrealistic problems set up. But that's not like you're trying to exercise, in particular for our case, we're trying to exercise what does classical relativity do to problems where you are thinking about them with energy, momentum, and the conservation of energy and momentum. So we're going to have two objects. This is in our thought experiment, are two objects that are identical. And what they look like is this. So each of them is like a little ball, and the little ball can report its own temperature. So we're going to have two of these things. Each of these things has the same mass because they're identical in every way. So mass m, and it reads its own temperature, right? So, for example, you might see a little 20. So it looks like it says, for example, 20 degrees Celsius. Let's say that the units that the little thermometer uses to report temperature is degrees Celsius. Okay, and it's a mass m. And we're going to have two of them, and they're going to have what's called an inelastic collision, right? But it's perfectly inelastic, right? So perfectly inelastic collisions are quite special. The point is you may start off with two of these objects that are completely separate. So we're going to, let's say this one is heading this way and this one is heading towards it. So they're going to have a crash. And what happens is afterwards, they are stuck to each other. Right? A perfectly inelastic collision is they are stuck to each other and move as one object. So this single object, if each of the objects that come in to the collision have mass m, then this new object has mass 2m, for example. And let's say that we had more motion towards the left, or momentum towards the left, than we had towards the right, so that after the collision, this 2m object is continuing to move towards the left, right? That's what you know happens in collision physics. So what's more is we're going to say that there is a head-on, perfectly inelastic collision. And another thing is there is no air, right? So no air resistance, no air friction, that kind of thing. So there's no air. And also, actually, no gravity. Let's say that they're not falling as they hit each other, right? So no gravity. This is a thought experiment, and I want a very simple setup. I don't want the complication of gravity. I don't want the complication of air resistance. I don't want the complication of them hitting each other kind of like off each other's axis so that they have a tumbling afterwards. Right? That introduces the complication of having angular momentum. I mean, there's angular momentum here, but it's just not interesting. Yeah. So I have a thought experiment, completely. I don't know, the most simple version of thinking about this. The unrealistic expectation of this thought experiment is maybe thinking about an object that can read out its own temperature, right? That it has some digital display. But I think it's interesting to have this digital display because I want to talk about the conservation, in particular, of energy. And you know that energy and temperature are related to each other. They're not the same thing, but they are related to each other. Okay, so this is our thought experiment. And I think that, yeah. So, yeah, so let me move on and continue with the thought experiment. All right, so I'm going to split this situation up into 3 pictures. In the first picture, this picture is called the center of mass, and it's referred to as a frame of reference. So this is the center of mass frame, and I'm going to give it a symbol. The symbol is this script O sub COM. So in the center of mass frame, we have a before and after. So before the collision, what it looks like is we have the 2 objects, right? So that's its little digital temperature readout, and so it's heading into the collision. I'm going to say that it has some initial motion v sub I, and of course it's an object of mass m. And if we're in the center of mass frame of reference for this system of 2 objects, then the 2 objects are moving with equal but opposite momenta. That's the this particular case. So so here is the identical mass moving with the identical speed, but in the opposite direction. Right? So this is before the collision. After the collision, and in particular, it's after the collision is completely finished. That is, you know, you could say that this is a long time after the collision. The 2 objects have met in the middle, right? So they've met here, and they are stuck to each other. Right? They are stuck to each other and at rest. Right? So before I have momentum here and momentum here. I've got kinetic energy and kinetic energy. But afterwards, I don't have any momentum. And afterwards, I don't have any kinetic energy either. And that's what will happen in the center of mass frame. Another frame of reference that's interesting is the initial rest frame of let's say it's object B, right? So this is called object A, and this is called object B, and this will be referred to as the frame of reference O sub B, right? But it's the initial rest frame of B. So what's that look like? So what it's got to look like is before the collision. So that's the initial situation, or yeah, so before the collision happens, the object A is coming in really fast. And in particular, I'll let you go and remember how these things go. But if I'm in the rest frame of B, then I could use velocity addition. Remember velocity addition from the previous video? Velocity addition connects these frames of reference. So I could move from this frame of reference up into this frame of reference with a velocity addition. So you would just have to figure out, right, what is the value of the velocity of A relative to B? And that gets you the data about the velocity of A actually being twice the velocity in that picture. So this is A, and here is object B, and B is at rest before the collision happens. But then after the collision is completely finished, we have A and B moving together, right, as a 2M object. And they are moving, actually, if you go and you do your collision physics, right, I have a total momentum in this frame of reference of twice, or m times 2v sub I plus 0, right? So that's 2 mvi towards the right. And so here, the answer to conserving the momentum, because there are no other forces involved in this problem, there's no air resistance, there's no gravity, there's nothing else going on in my thought experiment. So if I can, so the way that this plays out, the way that it must play out, is the way that conserves the momentum just of this system of two objects in the way that the total momentum does not change, right? That's the answer. So this is how the momentum does not change. So A and B are stuck to each other as a 2m mass object, moving at the combined, or moving in combination at a speed vi. So that's the answer from the conservation momentum. Interestingly, just really quickly, the kinetic energy in this center of mass frame equals 0 afterwards, and the kinetic energy in the center of mass frame is not equal to 0 before. But down here, the kinetic energy in the initial rest frame of B, because in this frame, right, B is no longer at rest after the collision, but this is the frame associated with B's initial velocity before the collision. So the kinetic energy of the combination of A and B is definitely not 0 before the collision, right, because I have a bunch of mass in motion. And then afterwards, I still have mass in motion, right? It's still not 0 in, let's say, O sub B, right? So this is the observer frame O sub B. So what if I instead take a third frame of reference, and this is the rest frame of A before the collision. So this we might designate as O sub A. And I bet you can see what it's got to look like. What it's got to look like is before the collision, object A is at rest, and object B is headed directly towards it at twice v sub I, right? This is object B, this is object A. And yeah, and then afterwards, the collision is going to happen right here. So after the collision, they're both over here somewhere. So here is A and B, but they are now a 2m object moving towards the left at speed vi. So kinetic energy in observer frame A is not 0 before, and the kinetic energy in observer frame A is also not equal to 0 afterwards. In fact, actually, if you think about it, what we have to have happen is that this point of view and this point of view are actually identical because of the symmetry that is the fact that A and B themselves are identical except for the motion. Yeah. So so these certainly seem like, especially if you look at the energy, what's interesting is the energy is different. And I hope you can see that. How can the energy be different? And what why I think this is important is center of mass observer, rest frame of B observer, and rest frame of A observer, they must note same temperature change and same damage. So temperature change and damage. So temperature change, what I'm referring to is the fact that earlier I said these little objects, they've got to report a temperature, and it's going to be some digital readout, right? So let's say they start off with 20 degrees, right? They start off identical. So two objects are identical. They have the same temperature. They're just headed towards each other for a collision. So let's say that observer, or the observer frame in the center of mass, notices that afterwards what you have is these two objects are stuck to each other, and they both read, for example, 22 degrees Celsius. Right? That's what observer COM sees. And in the center of mass reference frame, there is a certain amount of damage. And this damage is something that can be physically measured, like you measure the amount of deformation or something like that. The you know, how the size or the dimension of the thing changes or something. But the point is if COM sees this certain amount of damage and also sees the digital readout read 22 each, because neither of these things is going to be different in the center of mass, right? So they must read the same temperature. Then that means that the initial rest frame of B and the initial rest frame of C should also see the same damage and the same temperature change. So I'll say that this is a temperature change, right? Delta T, right? And these are energy issues. But I just showed you that the energies, well, at least between the center of mass and then either one of these frames of reference, the energies are different. What happens to the energy appears to be different. So, in our thought experiment, let's in particular check what happens to the energy. And in particular, what we want to check is, because there is no other type of energy, there's no sort of energy loss to, collisions with air molecules or whatever you say. And there is no change in potential energy associated with gravity. There is an energy here, but there is physical damage, right? It takes energy to cause damage. And there is an internalization of thermal energy, right? So somehow this external kinetic energy becomes internal energy associated with temperature change. Okay, so let's do that. So in the center of mass frame, so let's check kinetic energy. And let's do it for the center of mass frame of reference. So before the collision, I have the kinetic energy total is equal to 1/2 mvi squared, right? I've got mvi, has to be squared, and then I got a half, but that's for A. B also has kinetic energy. So this is A's kinetic energy before the collision, this is B's kinetic energy before the collision, and this totals up to mvi squared, right? That's for before. And I can also check what's the kinetic energy after the collision. So it's pretty easy to see the kinetic energy total. Well, there is no motion, so it's equal to 0. So what I mean by checking the kinetic energy in the center of mass is checking what happened to the kinetic energy. And it turns out that the kinetic energy total after the collision minus the kinetic energy total before the collision is equal to, right, 0 minus mvi squared. The idea is this energy, this kinetic energy, was converted to other forms. And the forms are damage and temperature change. And the amount that gets to go over to the other forms is mvi squared. So some fraction of this is associated with damage, and the remaining fraction is associated with temperature change. And that's what's meant by the conservation of energy. So the energy changed forms, but the point is the total amount of energy doesn't change. It just got converted. So to finish off this video, let's check in the observer frame where the object B was initially at rest. Actually, let me do it in A. I'm so sorry. So let's do it in A. And the reason I want to do it in A is because I can put the piece of paper up here, and this is data about A. Okay, so here's observer frame A. So before the collision, the total kinetic energy is equal to, so object A has no kinetic energy before because it's at rest, but after the collision I've got 1/2. It's only one of the m's, right? But it's moving at 2 times v sub I, and that thing needs to be squared. So this is 1/2 the mass of object B times the speed of object B squared, and the speed is twice vi, right? So that's the before kinetic energy. The after kinetic energy, so the collision results, so after the collision is finished, I have the two balls moving together. So they move together as an object with doubled the mass, but with the speed v sub I squared. So if I go and I just calculate out what this is, right, this is 2 squared is 4, but that 4 is divided by 2 over here. So there is a 2 left over, and you can do this on your own, but it's twice mvi squared. And over here, the total kinetic energy afterwards, if you calculate this out, so it's half of 2 goes to 1, and left over with mvi squared. And so the point is, though, is that the total kinetic energy has changed to by exactly, right? So this is the after minus the before. It's equal to minus mvi squared. And this is in the reference frame we're calling A. So can you see that these are the same? The idea is this is important. And the reason is because these two observation frames, or this is the physicist in the center of mass frame, and this is the physicist that was before the collision moving along with the object A. These two physicists arrive at a reason to see the same damage and also the same temperature change. So damage and temperature change must be invariant to frame of reference, right? So these are very basic physics things. That is, you know, like there's no way that these various observers could ever look at the digital readout and see different values. I hope you can see what I mean. Also, these different observer frames can't watch the collision happen and not detect the same amount of damage. That is, those two issues, right, in particular in this thought experiment, can't be discovered to be different by a really smart physicist in the center of mass and an equally competent, very smart physicist that happened to have moved along at a different relative motion. That is, these two physicists must see the same physics play out when they watch the same set of events happen. And that's the big idea. This is very much a physicsy thing to say, right? That different observers cannot have a variation in the outcome of a particular experiment. Yeah, but what's interesting is they definitely measured different values of kinetic energy. They would have measured different values of the total energy of the systems. They had different individual values for the momentums. Yeah, so that's sort of the main idea.